Yeah, by all means.
Okay, so welcome everyone to the afternoon session. So we have three talks lined up for this session. The first talk is by Bindusar Sahoo from ISM2021, and he'll be speaking on rudiments of n equal to 3 supergravity in 4 dimensions. Okay, so over to you, Bindusar.
Okay, thank you, Bobby. And thank you, Alok and all the organizers of ISM 2021 to give me an opportunity to speak, and also for arranging this nice online meeting. Okay, yeah, it's nice to meet you all online, although we would at some point like to meet also physically. Okay, so today I'm going to speak about rudiments of n equal to 3 conformal supergravity. Okay, so there is two parts up to this. First is n equal to 3 and then conformal supergravity. So let me first tell you why do we need to worry about n equal to 3 supergravity. Okay, so I mean, it's quite well known that if you take a non-gravitational CPT invariant n equal to 3 supersymmetric theory, then there's always a fourth supersymmetry and the theory becomes n equal to 4. So, I mean, so there is no genuine CPT invariant pure n equal to 3 theory. So if you take any CPT invariant n equal to 3 theory, it's always n equal to 4. And this can be understood by analyzing the representation of the n equal to 3 supersymmetry algebra. In particular, if you look at the multiplet of massless states with maximal spin 1, and if you add the CPT conjugate, you always get a representation of n equal to 4 supersymmetry. Okay, and this means that the n equal to 3 vector multiplet is the same as n equal to 4 vector multiplet. And however, once you have gravity in the picture, this is no longer true. Okay, and in fact, the massless representation of n equal to 3 supersymmetry algebra with maximal spin 2 is different from n equal to 4. Okay, although one cannot have a genuine CPT invariant n equal to 3 supersymmetric field theory Lagrangian, there have been some studies on this so-called pure n equal to 3 superconformal field theories using techniques from holography, and these are some of the reference. So this reference by Aharoni and FTKF from 2015, they basically assume that suppose there is a pure n equal to 3 theory, so what would be its so-called properties? And these people in this paper in 2015, they explicitly constructed a n equal to 3 superconformal field theory, and which satisfied also all the properties that was discussed in Aharoni's paper. And as expected, these do not have a Lagrangian, so these are kind of non-Lagrangian theories. Hence, study of n equal to 3 supergravity is important if you want to understand the holographic goal of such theories. And there have been work going on in this direction. So n equal to 3 supergravity has been understood from a different perspective, the so-called group manifold approach. And yeah, there was a paper in the early 80s by Castelloni and his collaborators, who looked at matter coupled n equal to 3 supergravity theory from this group manifold approach. So why do we need to worry about this conformal supergravity approach is the following. So so why do we need to worry about conformal supergravity? Because conformal supergravity plays a vital role in the construction of these matter coupled supergravity theories with higher derivative corrections. So in the other approaches, in the group manifold approach, it's hard to construct high derivative corrections in a systematic manner, and conformal supergravity gives us a nice framework to construct these supergravity theories with higher derivative corrections. And if you want to also learn about ADS-CFT correspondence, where the supergravity has high derivative corrections, we would like to construct such supergravity theories with high derivative corrections, and therefore we worry about conformal supergravity. Okay, and why is that? I mean, because essentially conformal supergravity has more symmetries, and so this large high degrees of symmetries, this allows the degrees of freedom to be arranged in shorter multiplets, and this makes the problem of constructing matter coupled supergravity theories, including high derivative corrections, quite tractable. And finally, one can use some of these matter multiplets as compensators to gauge fixed additional symmetries. To go from conformal supergravity to the physical Poincare supergravity. So there is a systematic procedure to do this. And in the pre-learn session, I think Madhu talked about some of these techniques called superconformal multiplet calculus. Okay, so I will briefly discuss about them. Okay, so so basically conformal supergravity, has this gauge equivalence program. I mean, you can think of conformal supergravity as a gauge theory. Okay, so what you do is you essentially start with, if you are interested in an extended conformal supergravity, you start with the gauge theory based on the superconformal algebra, SU2,2/n. So SU2,2/n has a number of generators. In particular, if you're interested in n equal to 3, these are the generators of SU2,2/3 algebra. So this is the local translation, this is local Lorentz transformation, this is a spatial conformal transformation, this is dilatation, and there are two R symmetries, U1 and SU3, and there is one ordinary supersymmetry, and there is a spatial supersymmetry because it's in a superconformal algebra, so there is a spatial supersymmetry. And corresponding to all these generators, you have a bunch of gauge fields and field strengths. Okay, so this is the gauge theory, and as Madhu discussed earlier, so in order to convert this gauge theory into a theory of gravity, we need to impose some constraints on the curvature. So for example, we need to impose this constraint that the curvature associated with the local translation has to be set to 0. So that basically converts the local translation into a general coordinate transformation. Okay, and because we are in a superconformal theory, so we need some additional constraints also. And these constraints essentially make some of these fields dependent. So for example, this constraint will make this omega mu AV dependent on E mu A and other fields. Okay, and you can interpret, you will get the standard interpretation of this as a spin connection and this as a well bind, which we want in a supergravity theory. And this constraint will make this gauge field corresponding to spatial conformal transformation also dependent. And this constraint will make the gauge field corresponding to the S supersymmetry dependent. Once you do this, you count the number of degrees of freedom, you will see that the bosonic and fermionic degrees of freedom are not matching if you have n greater than 1. And therefore, you need to complete the field representation by adding additional auxiliary fields. And you have to accordingly also modify the superconformal algebra. And in this modified superconformal algebra, the structure constants actually becomes field dependent and they become structure functions. Such superconformal algebra are known in the literature as soft superconformal algebra. And in this whole procedure, the multiplet that you have obtained, which basically includes these gauge fields and the additional auxiliary fields, that they are known as the Weil multiplet. Okay. Now we'll discuss about n equal to 3 Weil multiplet. Because to understand n equal to 3 conformal supergravity, you need the n equal to 3 Weil multiplet. So as we discussed, we need some additional auxiliary fields to close the Weil multiplet. And typically, these additional auxiliary fields are found by the so-called current multiplet method, wherein you find the current multiplet for a rigid multiplet, for example, the vector multiplet. Okay. And this current multiplet couples to the linearized Weil multiplet. And therefore, the components of the current multiplet and the transformation loss gives us the linearized Weil multiplet along with the auxiliary field content. Okay.
I have a question.
Yes.
Does this Weil multiplet have a superfield representation? Can it be derived from some D term of some?
Exactly. You can write a superfield representation. In n equal to 2, it is very easy to write. It's basically a chiral superfield. For n greater than 2, it is a little bit complicated, but you can do that. Okay. But no, we will work in the component method. We will not go to the superfield. Okay. So yeah. So in this way, you will obtain the linearized Weil multiplet along with the auxiliary field content, and then you just have to run the crank and complete the full nonlinear transformation of the Weil multiplet and the superconformal algebra. Yeah, so that is the technical part. But this is the current multiplet approach is the way to construct this Weil multiplet. However, as we have discussed earlier, in n equal to 3, there is no genuine vector multiplet, which is a different vector multiplet. Like as I said, the n equal to 3 vector multiplet is the same as n equal to 4 vector multiplet. And therefore, if you take a rigid n equal to 3 vector multiplet and try to obtain its current multiplet, you will get the same current multiplet as n equal to 4. And therefore, if you couple it to some linearized Weil multiplet, it will be the n equal to 4 Weil multiplet. Okay, so it doesn't help to construct the n equal to 3 Weil multiplet. However, in 2017, Van Proijn and Van Muyden, they found a way to overcome this hurdle. So what they did is, instead of constructing the n equal to 3 current multiplet from an n equal to 3 rigid vector multiplet, they truncated the n equal to 4 current multiplet directly to n equal to 3. And in this way, they obtained the n equal to 3 while multiplet. Okay. And these are the field contents of the n equal to 3 while multiplet. So these are the gauge fields that we had discussed earlier. This is the Weyl-Bind. This is the gauge field corresponding to dilatation. This is the gauge field corresponding to the SU3R symmetry and U1R symmetry. And these are the auxiliary fields that we need. These are the bosonic auxiliary fields. And these are the fermionic auxiliary fields. And this is the gravity. Okay. And these are the dependent gauge fields as we had discussed earlier. So this is the n equal to 3 while multiplet that was constructed by these people in 2017. Okay. Yeah. So after we have obtained the n equal to 3 while multiplet, the next step is to obtain an action for this while multiplet. So we are interested in this n equal to 3 Kaufman supergravity action for the while multiplet. Okay, and so now I'm going to discuss how to construct this action. And this is from our recent paper with Subramania Hegde and Madhu. Yeah. So in order to construct actions in Kaufman supergravity, one often resorts to well-known density formula. And this is something also Madhu has discussed in the pre-learn session. So density formula are invariant action given in terms of some simple multiplet. For example, in n equal to 2, Kaufman supergravity, one has chiral density formula. And this is even in terms of chiral multiplet, or you can have a linear vector density formula given in terms of a linear and vector multiplet. So chiral density formula is very simple because, in n equal to 2 chiral multiplet, if you see, the highest component of the chiral multiplet under supersymmetry transforms into a total derivative. Okay, and therefore, if you write down a Lagrangian density, which is just proportional to the highest component of this chiral multiplet, you get an invariant action. Now, this is in rigid supersymmetry. If you have supergravity, you just need to add terms, systematically add terms proportional to gravity, to make it invariant. And this has been done, and this gives us a well-known chiral density formula. And same with the linear and vector multiplet also. And once you have this density formula in terms of these multiplets, and you want to construct invariant actions in n equal to 2 Kaufman supergravity, for example, invariant action for the while multiplet, what you need to do is basically you need to write down a chiral multiplet whose fields, whose components are basically composite expressions of the while multiplet or the vector multiplet, right? And once you do that, and you basically substitute this embedding in the chiral density formula, you get an action for the while multiplet or the vector multiplet. So this is a standard approach that was followed for n equal to 2. But this approach kind of breaks down for n greater than 2 because this chiral density formula does not have a nice generalization to n greater than 2. Yeah. So in order to overcome this hurdle, earlier in our study of n equal to 4 Kaufman supergravity, as mentioned in these papers, we found an action principle based on something called the method of superforms, which can be used to construct density formula. So we don't really rely on some well-known density formula. We can actually construct density formula based on this action principle. And from this density formula, we can construct invariant actions. So we started this method for n equal to 4. Okay, but this method can be applied to any supergravity theories. So not only for n equal to 4, we also found its application in n equal to 2. So in this paper with Subramania Hegde, we found new density formula in n equal to 2 and new actions in n equal to 2. So which are not constructed from a chiral density formula or a linear vector density formula.
I have another question.
Yes.
So if you have the superfield formulation for while n equal to 3 while multiplet, why can't you simply directly construct the action by taking the D term, by taking some...
It's not, as I said, first of all, for n equal to 3 is a very recent thing. I don't think anybody has found, I think n equal to 3, supergravity is known in kind of harmonic superspace.
Yeah.
It's a bit complicated. It's not like n equal to 1 and n equal to 2 where you just take the D term and get the action. It's a little bit more complicated than that. I mean, eventually, people have studied n equal to 4 in Kaufman superspace, but nobody had n equal to 4 Kaufman superspace, nobody had studied. N equal to 2 people have studied in superspace language. N equal to 4 is n equal to 3 and n equal to 4. These are not as straightforward as n equal to 1 and n equal to 2. So it is not like taking the, I mean, in n equal to 4, of course, the superfield formulation is known, but n equal to 3 is not known. I mean, it's just started. I mean, 2017 only the Weil multiplet was constructed. Yeah.
But can't you get down from the n equal to 4 formulation to the n equal to 3 formulation as we were talking about?
Yes, we can do that. And in fact, yeah, we can do that. But it's not, as I said, n equal to 4 also, the superfield formulation is not very straightforward. I mean, we cannot write down an action in superfield formulation. I mean, the action that we wrote down in this paper, we had to resort to component methods. In superspace, maybe it's possible, but it's not known till now.
Okay.
Okay. Right. So this action principle actually follows from a very simple observation in differential geometry. So this is the principle. Let me explain it using the language of differential geometry. So consider a d-dimensional manifold curly M. Okay, it's a larger manifold. This capital D is a larger manifold, and in that manifold you have a small d-dimensional submanifold M. Okay. And let us consider the integral of a D form on this submanifold. So you consider this integral on this submanifold. Okay, J is a D form, and you are considering this integral on this submanifold. And under arbitrary diffeomorphism in M, so under arbitrary diffeomorphism in this larger manifold, this D form transforms as a Lie derivative. So this is the transformation of this D form. And as we know, Lie derivative is just the anti-commutator of the exterior derivative and the interior product, and that's what it is. Okay, so if this action has to be invariant under arbitrary diffeomorphism in M, okay, I mean this action just by being a D form in M, it is already invariant under arbitrary diffeomorphism on M. But if we want this to be invariant under arbitrary diffeomorphism in this larger manifold, then it is clear from here that dj has to be 0, because the transformation of J has a total derivative piece. So if this manifold is has no boundaries, or even if it has boundary and a nice fall-off condition for the fields, this will eventually go away. But to make this 0, you need dj to be equal to 0. Okay, so this action would be invariant under the full diffeomorphism on this M if dj is equal to 0. Okay, that's what I've written here. So if you require the invariance action of the action under arbitrary diffeomorphism in this larger manifold, you would require dj to be 0. So that is j to be a closed form. Okay. So now we would be interested in the case where the submanifold M is actually the full space-time manifold, and this larger manifold is a manifold where some gauge symmetries have been geometrized. Okay. So in this formalism, if you are able to construct this action integral, which is also gauge invariant. So now gauge transformation becomes a diffeomorphism in the larger manifold, right? Because you have geometrized these gauge symmetries. So ensuring gauge invariance of this action would basically mean ensuring diffeomorphism invariance of this action in the larger manifold, and which basically boils down to finding a closed form J in the larger manifold where you have geometrized these gauge symmetries.
One question. Sorry to interrupt. This formalism of this action principle, it seems quite general. So the chiral density formula for n equal to 2, that cannot be derived from this.
Yes. That can be derived from this. That can be very easily derived from this action principle. Yeah.
Okay. And you can derive other density formulas apart from the chiral one.
Exactly. So it can already derive the already well-known density formula. Other than that, it gives us a framework to derive more general density formula and hence more general actions.
Yeah. But those will all be like independent density formulas, or
yes, they would all be like independent density formula. Yeah.
Okay. Thank you.
Okay. So now, So basically, as I said, if for constructing gauge invariant actions, you need to geometrize these gauge symmetries, and you need to find a D form J which satisfies the closure condition. And in particular, for constructing supergravity action, supergravity is also a gauge theory, you need to geometrize supersymmetry and impose the closure condition. Okay. So what you need to do is basically you need to start with the larger manifold where supersymmetry has been geometrized. Okay, so these are the coordinates of your larger manifold N. Okay, so the x mu are the coordinates of this smaller manifold, which is the space-time manifold, and these are the extra coordinates that you add to geometrize supersymmetry. And the super Vielbein one forms of this larger manifold are this basically. Okay, so these are one forms basically in the larger manifold. So it has legs not only along the space-time direction but also along the theta direction. Okay, so however, I mean, if you truncate it to the space-time manifold, then these are your standard Vielbein and standard gravity now. Okay, so what you now need to do is you need to construct a fourth form, okay, which satisfies the closure condition. Okay, as if you can find such a fourth form, then this action integral evaluated on the space-time manifold would be invariant under supersymmetry. Okay, so this is what we need to do. However, as we had discussed in superconformal gravity, apart from supersymmetry, there are a bunch of other gauge symmetries, like S supersymmetry, local Lorentz transformation, R symmetries, etc., etc. So, but these symmetries are very easier to realize. They are not like the ordinary Q supersymmetry, which is harder to realize. These symmetries are easier to realize. So we will not geometrize these symmetries to find invariance under those symmetries. So we will only geometrize the Q supersymmetry, and the other symmetries we will ensure that they are invariant by explicitly demanding that this fourth form that we are constructing is manifestly invariant under these symmetries. Okay, so therefore the action becomes manifestly invariant under these other symmetries, and the invariance under the Q supersymmetry is realized by ensuring its closure condition. But now, since J is manifestly invariant under the other symmetries, the closure condition, I can replace it by this covariant closure condition, where this covariant exterior derivative is covariant with respect to the other gauge symmetries. Okay, because J is manifestly invariant under those symmetries, so dJ is the same as nabla J, and so we can instead demand nabla J equal to 0. I mean, the reason why we are doing this is because it gives a nice systematic way to carry out our work. Otherwise, this is the same as dJ is equal to 0. Okay, so now, and then we need to take an answer. So since it is a fourth form, okay, we expand it as wedge products of the super Vielbein one form. So I have, not written the wedge products explicitly, but there is a wedge product in between these one forms. Okay, so these are our super Vielbein one forms, and our super Vielbein one forms are basically this Vielbein one form and the gravity one form. And now when I expand it out, I have this whole bunch of terms with 4 gravity with 3 gravity and 1 Vielbein, 2 Vielbein, 2 gravity and so on. Okay, so this is our answer, and we need to find a J such that it satisfies this covariant closure condition. Okay,
I have a question.
Yes.
These super Vielbeins are superfields, right? They are superfield constructed out of the EAs and the Xis, right?
Exactly. So in the larger manifold, where we have geometrized supersymmetry, I mean, you can think of that larger manifold as a super space. So the super Vielbeins are basically superfields. Okay, so these are all superfields. So these take values in the larger manifold where we have geometrized supersymmetry. Okay, but when we actually construct the action, we are writing down the integral of this fourth form on the space-time manifold. So when we truncate the super Vielbein on the space-time, they become the standard Vielbein and the gravity. Okay, so
is the understanding that you take this G, DCBA, EA, EB, EC, ED, and then you integrate over the thetas or something like that? No.
We are basically taking this. So
by the thetas, I mean the Grassmann.
No, we are not integrating over the super. So this is our action. So we are integrating this fourth form J on the space-time manifold. Okay, and our space-time manifold is basically defined as a larger manifold with this truncation, theta equal to d theta equal to 0.
No, what I'm worried about is, in general, you would have.
I think, please, can I suggest that we keep discussions for the discussion session? Because I think we have been, don't mind, but we have been running over time. So let's, only short questions, I think, should be allowed during talks.
Yeah, okay, we can discuss this in the discussion session. Yeah, you can ask me during that time. Yeah, so yeah. So this is, so this is the answers, and we need to impose this covariant closure condition. So we need to know how this covariant exterior derivative acts on all these objects that are appearing in the answers. Okay, we need to know how this covariant exterior derivative acts on this Wheelbein and the gravity in one form, and also on these objects, JDCBA, which are basically super covariant objects. So these JDCBA are super covariant objects. Okay, so its action on the super Wheelbein is well known if you understand the Weil multiplet, because that is given by this super torsion 2 form. Okay, and this is this we know because we understand the Weil multiplet, and this is the result. This is the result for the action of the covariant exterior derivative on the Wheelbein 1 form and the gravity in 1 form. Okay, so these are given. So these are all 1 forms, and this exterior, this wedge product is implicit in this equations. Okay, and on the super covariant.
5 minutes.
Okay. And on the super, so there were some questions, so maybe take some extra time.
Yeah, sure. Okay,
so on the super covariant blocks, the covariant exterior derivatives acts like this. Okay, so so this is basically the super covariant derivative of this covariant object, and this is the delta alpha. This nabla alpha is the supersymmetry generator. So you can think of this part as a supersymmetry transformation of this object, where the supersymmetry parameter has been replaced by the gravity no 1 form. Okay, so that is essentially what this covariant, how this covariant derivative acts on the super covariant object JDCBA. Okay, and when you impose this nabla j equal to 0, this basically relates these different blocks appearing in that answers to each other via supersymmetry, and also imposes some constraints. Okay, so and this actually gives us this action integral. So you can think of this JDCBA, all these JDCBA, as some component of an abstract multiplet, in terms of which we have this action. Okay, and these components are basically related to each other via supersymmetry, which is ensured by this closure condition, and also satisfy some constraints, which also come from this closure condition. And this is what we call as a density formula. Okay. Yeah. So in order to get an invariant action, basically you need to find these blocks JDCBA, which forms a component of an abstract multiplet, in terms of the multiplet for which you want to find the action. For example, if you want to find the action for the Weil multiplet, you need to find these objects in terms of the fields in the Weil multiplet. Okay. So in n equal to 3, so the answer is basically, the starting point of the answer is basically you have to tell what is the answers for this J, which comes with the maximum number of gravity. It turns out that for n equal to 3, the answers that comes with the maximum number of gravity needs to have this structure. Okay, where CMN, this is symmetric in M and N. These are my SU3 index. Okay, and then imposing this closure condition, you would find that the Cij needs to satisfy these conditions. So this basically tells that in the left supersymmetric transformation of this object Cij, there is nothing in transforming in the 15 of SU3. And this tells us that in the right supersymmetric transformation of Cij, there is nothing that transforms in the 10 of SU3. Okay. And now in order to find an action for the n equal to 3 Weil multiplet, we need to find a Cij in terms of the Weil multiplet fields that satisfy this constraint. Okay. And you take the Weil multiplet fields and try to find this composite expression. You find that the composite expression has this structure. Okay, with some overall constant which can be complex. Okay, and if you take alpha equal to 1, this leads to the supersymmetrization of the Pointryagin density, and if you take alpha equal to I, this leads to the supersymmetrization of the Weil square term. Okay, so in this way we can find the n equal to 3 conformal supergravity action, which is a linear combination of the Pointryagin density and the Weil square term, supersymmetrization of that. Okay, the action is quite big, so I'm not giving it here. Okay, but this is essentially what we find.
Bindusar, it's almost time, so maybe in 5 minutes or so.
Just some future directions. I will just finish.
Sure.
Okay, so what next? So next, in the next step, we would like to go from conformal supergravity to Poincare supergravity. So we have already seen the construction of conformal supergravity. Okay, so as we had discussed earlier, in order to go from conformal supergravity to Poincare supergravity, we need what are known as compensating multiplets. Okay, so these are the multiplets that you need to gauge fix the extra symmetries that are present in the in conformal supergravity. Okay, and also eliminate the auxiliary fields that we had in the Weil multiplet, and okay, then you go from conformal supergravity to Poincare supergravity. It turns out that in n equal to 3, you would need at least 3 vector multiplets to play the role of compensators. One can also add additional vector multiplets, which will play the role of matter multiplets in n equal to 3 Poincare supergravity. Okay. And now n equal to 3 vector multiplets and its coupling to conformal supergravity can be obtained systematically by truncating the n equal to 4 vector multiplet coupled to conformal supergravity that was obtained by Day-3 in 1984. Okay. I'm loosely using the word truncating here. It's not actually truncating. As I said earlier, n equal to 3 vector multiplet is the same as n equal to 4 vector multiplet. But by truncating, I'm basically saying that I'm rearranging the degrees of freedom. So the degrees of freedom are the same in n equal to 3 vector multiplet and n equal to 4 vector multiplet. So by truncating, I am basically rearranging the degrees of freedom of n equal to 4 vector multiplet to n equal to 3 vector multiplet. Okay. And just like n equal to 4 vector multiplet, the n equal to 3 vector multiplet is also an on-shell multiplet, meaning the commutator of supersymmetry transformation on the n equal to 3 vector multiplet does not close without using the equations of motion. So you have to use the equations of motion to close the algebra on n equal to 3 vector multiplet. It's just like n equal to 4 vector multiplet. And these equations of motion are you can also obtain by this systematic truncation of the n equal to or rearrangement of the n equal to 4 vector multiplet. So all these things we have obtained already, and eventually one can obtain an action for this n equal to 3 vector multiplet by using this previously discussed density formula and the equations of motion. So we have to also use the equations of motion because the density formula is blind to the equations of motion. So it will give us action where the equations of motion has been eliminated. So terms proportional to the equations of motion has been eliminated. So we have to basically use the action constructed from the density formula and the equations of motion to construct the genuine action for n equal to 3 vector multiplet coupled to conformal supergravity. And this is actually a work in progress with Devanshu, Madhu, and Subramanya. And then we basically use this action for the vector multiplet to go from n equal to 3 conformal supergravity to Poincare supergravity. Yeah, so this is some work in progress. And apart from that, there are some other work that we would be interested in. You know, as I said, the prime motivation of studying n equal to 3 supergravity is ADS-CFT correspondence. So what we have discussed so far is the construction of ungauged supergravity. Whereas for ADS-CFT correspondence, you would like to have a gauged supergravity. That is what I mean. We would like to study, and there are some more directions related to the double copy. So maybe I can go through this if somebody asks question, but maybe since I'm run out of time, I can stop here. Thank you.
Okay, thank you. Any questions? Yeah.
Bobby, can I ask a small?
Yeah, sure. There's wanted to ask a question, then maybe after that.
Yeah. No, go ahead, Alok. I can ask later.
No, I just wanted Bindusar to say something about the double copy that you couldn't finish if you.
Yeah, sorry. Yeah. Yes. Yeah. So basically.
Actually, if it will take too much time, then we can have.
Okay, sure.
No, it will not take too much time.
Oh,
so basically what has been shown for n equal to 0, 1, and 2, and 4 conformal supergravity by Johansson and his collaborators, is that there is a double copy structure for this n equal to 0, 1, and 2, and 4 supergravity. That structure is basically this. One copy of the gauge theory is this so-called df square min, and the other copy is this super Yang-Mills. Equal to 1, 0, 1, 2, 4 super Yang-Mills. So this df square is a gauge theory that is purely made out of dimension 6 operators in d equal to 6 counting. This is the Lagrangian for df square gauge theory. where you have some scalars in some representation of the gauge group. And this df square mean is basically just the kinetic term, nothing else. So if you have the df square mean in one of the gauge theory, then what you get is basically conformal supergravity. If you replace the other one,
right. Okay. I see.
Yeah. So we would like to see this for n equal to 3 conformal supergravity also. But the point is that there is no n equal to 3 super Yang-Mills Lagrangian, as I had discussed, because you cannot have a genuine n equal to 3 super Yang-Mills Lagrangian. So whatever n equal to 3 Lagrangian you write down, it becomes n equal to 4. So all these n equal to 3 super conformal field theories have been understood from a non-Lagrangian point of view. So we really don't know how to address this question because we need, to understand this double copy, we need a Lagrangian.
But the perturbative amplitudes you have computed in your conformal supergravity to 3 level, or
yeah, that can be computed. We have not computed. We have just written down the action. But Hansen and all these people have done for all these other conformal supergravity. Basically, they computed the amplitudes for this double copy.
Yes.
From the amplitude, they basically constructed the conformal supergravity action in some
right.
And they matched that with the conformal supergravity action.
Right. Yeah, it goes from the amplitude side. That's why I was asking. Yeah. Thank you. I think yeah.
Ritabrato, you have.
Whether I've understood correctly that I want. So in the last part, you commented that in writing down the n equal to 3 action, we didn't have to impose the equation of motion, right?
Vector multiplet. Yes.
Yeah. But like when you are writing S as integral of J over M, you are using the fact that J is a closed form, right? So
Right. So J will be a closed form. So as I said, so we have to impose this nabla J equal to 0. So when we actually do that, so this J, the blocks, the J had various blocks, right? This J, D, C, B, A.
Yeah.
So when we impose this nabla J equal to 0, this various blocks gets related to each other by a supersymmetry, and also there are some constraints that are imposed on these blocks. Okay, so typically, if you ensure only a preliminary set of constraints, then the other constraints are satisfied just by demand if the supersymmetry algebra is closed. Okay, but if you have an on-shell multiplet, the supersymmetry algebra is closed on this on-shell multiplet up to equations of motion. So what I'm saying is, because of this, so the action that you will construct from the density formula will be blind to the equations of motion. So they will be proportional to the equations of motion that the action will simply eliminate from your.
Okay.
If there are some terms proportional to equation of motion in the action which should be there, this action principle